Okay, so the lesson today is on graphing exponentials. So far, we have learned a couple of things. We have learned that a linear function forms a line, right? Okay. We've also learned that a quadratic function forms a parabola. Whether it be that way or upside down, it forms a parabola. That's a quadratic function. Okay. Now we're going to, we have done some with polynomials where we saw some cubics and quartics, but just briefly to just kind of talk about some characteristics of graphs. But the next one we're really going to focus on is an exponential function. And an exponential function looks something like this. It can go that way, or it can go, there's another way it can go, but it looks like that. It never is going to turn and come back up like a quadratic. This is what an exponential function looks like. Okay, so let's go ahead and start the lesson, and you're going to see that we're going to have some of our exponent rules come back into play that we've got to remember. So let's go ahead and take a look here at the first one. So we have all these x values, and we're going to plug them in. And by the way, notice that an exponential function, the exponent is the variable. Okay, with a linear function, we had x to the first power. With a quadratic function, we had x to the second power. With an exponential function, our power is the x. Okay, so what we're going to do is we're going, and let's put this out to the side. So if we copy down what we have in parentheses 2, that's coming from right here. That's coming from the function. The function is 2 to the x power. So we're going to take 2 to the, and x is negative 2 here. Now, just as a reminder, this 2 is really over 1, right? And remember, when you have an exponent, it's negative. Now, there's a lot of justification of how this works, but in the short and simple of it, when your exponent is negative, you flip the fraction so that the exponent can become positive. You recall that a little bit? Okay. All right, then, now we need to square 1/2. Well, 1/2 squared means the numerator is 1 times 1, and the denominator is 2 times 2. So that would give us 1/4. Okay, let's do the next number in the chart. 2 over 1, or 2, to the negative 1 power. Okay, remember it's the exponent that's changing because that's what the variable is. The x is the exponent. So this changes to 1/2 to the positive 1, which anything to the first power is just itself. So 1/2. Okay, then we have 2, or 2 over 1, to the 0 power. What is that? It's been a little while.
1.
1, good. Anything to the 0 power is 1. Then we have 2 to the first power. This is a positive 1, which is just 2. And 2 to the second power, which is 4. Okay, and then all we're going to do is plot these points, and you will have your exponential function. Okay, so we're going to be making a bunch of tables today, and then we're going to plot our points. Okay, all right, so the only thing new really for you is getting used to remembering your exponent rules with the negative exponent. Okay, so if you look at your x and your y, your x-axis, those are small numbers, and the y-axis are also small numbers. So my suggestion might be, or maybe I should ask you what your suggestion is. Do you have any suggestions when we come to graphing this? That's a straight line right there. Yes?
Go by 4s?
Ooh, I wouldn't count by 4s. 4, 8, the highest number we have is 4. On the x-axis, I would just go by 1s. Or no, you know what, we only have to go out to 2. And here the highest we go is 4. So why don't we count by halves, by 1/2, by 0.5s on the x and on the y. You don't always have to do the same for both, but because both of our x and our y, our ordered pairs are small. So I'm going to put a little note out to the side that says by 1/2. And because it's out to the side, that's understood that I'm going to go by 1/2 for both the x-axis and the y-axis. If you only wanted to go by 1/2 on the y-axis, then you would need to make that clear in your assignment. that your x is going by this and your y is going by something different, okay? All right, so I'm not going to go in. I'm not going to write all 0.5, 1, 1.5. Because I have it out to the side, I'm good. So let's go ahead and plot our points. So the first one says -2. Well, because we're going by 1/2, we actually need to go over how many? 4, and then up 1/4. Well, up 1 would be up 1/2. So a fourth is just half of the way there, right? So I just put it right there in the middle between the x-axis and the first spot. Okay, and then the next one is -1 and then 1/2. So basically over 2 and up 1. Okay, and then 0, 1. Well, we don't really just go up 1. We go up 2. And then 1, 2. So we go over 2 and up 4. And then 2, 4. And you get that. Are we okay so far? Okay, now, I want you to be very careful when you go to draw this, okay? Now, we know from other graphs that we don't just connect the dots like this and stop. We don't do that, okay? So you need to continue it on kind of like this, and then this one right here at the bottom just kind of keeps going. It doesn't actually level out, although in my picture it definitely looks straight. It looks like now it's constant, but it doesn't. It really continues to get closer and closer to the x-axis without going over, okay? And the positive, it continues to go up and up and up slowly. So that's what it's going to look like, okay? All right, let's do another one. There's some observations we're going to make here in a little bit, so I don't really want to say too much. I want you to kind of make some associations here as we move along. So let's do the next chart. All right, so we've got 1/2 to the what power? -2. Now, we know that we have, because it's got a negative exponent, we need to flip this to be +2/1, right? To the +2, which would be what? 4. Okay? 1/2 to the -1 is going to give me 2 to the +1, which is just 2. 1/2 to the 0 power is just 1. 1/2 to the first power is just 1/2, right? And 1/2 to the second power would be what? 1/4. Remember, you got to do the 2 times 2 on the bottom. Okay, so we're going to graph this. And we're going to count by 0.5s. Is that what yours looks like? Okay. So how are the graphs in number 1 and number 2 related? You want to take a observation here, Nicholas?
They're opposite.
They're opposites. Okay. Do you notice in the chart we have the same x values, right? The y values are reversed, correct? Okay, so write yourself some little note. The y values are similar, but the y values are there for different x values, right? Somehow make yourself a little note of that. You don't have to write exactly what I said. Okay. All right, let's take a look at number 4. All right, so this function says y equals 2 to the negative x power. So we have 2 to the, okay, and when it says negative x, that means the opposite of x, right? Yeah. Okay, so we're going to put opposite of negative 2, because that's what we're plugging in, right, is a negative 2. Okay, so the opposite of negative 2 is really just 2 to the second power. It's just a positive 2. And 2 to the second power is 4. All right, 2 to the opposite of negative 1 is 2 to the first power, which is 2. 2 to the opposite of 0, well, that's not possible. It's just 0, which is 1. 2 to the opposite of 1, what do we do here? We have to change it, and we have to flip the fraction. Remember, so it becomes 1/2 to the positive 1 now, which is just 1/2. And then 2 to the negative 2, which is 2 over 1, becomes 1/2 to the second power, which is 1/4. I would say that's the biggest thing, is remembering again what to do with the exponents. It's those rules again. So here we're having to apply the rules, okay? All right, so let's go ahead and graph. I would say we should do the same. What do you think? Count by 1/2. You know what, though? I didn't label that on this number 2. You always need to write it by 1/2. And then okay. And then just plot the points. I don't think you really need me to tell you. You can plot points. All right. And then we're going to do number 5. We ready for number 5? Okay. All right, so this one is 1/2 to the negative x. So 1/2, instead of 2 to the negative x, now we're going to do 1/2 to the negative x. So 1/2 to the negative 2 is 1/2 to the second power, which is 1/4. The next one is 1/2 to the opposite of negative 1, which is 1/2 to the first power, which is 1/2. Then 1/2 to the 0 is 1. 1/2 to the negative 1 power, that switches to what? 2 over 1, right? So just 2. And then 1/2 to the negative 2 switches to 2 over 1 squared, which is 4. Okay. Finding anything interesting? Let's graph this and then we'll chat. Yes, let's go by 1/2 again. Okay. So number 6 says the graphs for number 1, 2, 4, and 5 should be matched into 2 pairs of the same graph. Which equations match and why do they match? Okay, so who can tell me which equations match up? You can look at the graph, you can look at the table. Hannah?
Number 4 and 2.
Okay, so number 2 and number 4 match up. And number 1 and number 5 match up. Do you notice that? right? Okay, so interesting. The graphs, or the equations from number 2, the equation from number 2 says y equals 1/2 to the x power, and number 4 is y equals 2 to the negative x power. Let's start there with that one. And we're going to make a little note here. All right, so you should easily be able to see and understand that because of this negative exponent in number 4, that we ended up having to switch it around. But just so you have some notes, let's take number 4's function, so 2 to the negative x, and let's rewrite that as 2 to the negative 1 with the x outside, because negative 1 times x is a negative x, right? Okay, so I can take it and break it apart like this and write it this way. And then when we do that, we know that 2 to the negative 1 is written as 1/2, right? With the x outside, which is the other function now. See how you move from one function to the next? They're the same function because of the rules with exponents, negative exponents. Okay, so keep that in there. And let's do the same thing with 1 and 5 real quick. Function 1, I think, was 2 to the x power. Okay, and 5 is 1/2 to the negative x power. All right, so let's take that 1/2 to the negative x power. Let's rewrite it as 1/2 to the, I'm going to have to do this so it looks better, negative 1 with the x outside. I just wanted to use the parentheses there because it would look weird if I did 1/2 to the negative 1 power without putting the 1/2 in parentheses. And then you know that 1/2 to the negative 1 means we're going to switch it, so it'd be positive 2 over 1, or just 2, to the x power, and that's the other function. So that's why they're the same, is based on our exponent rules. So all exponential functions aren't always going to give you the same tables. I just wanted you to see how the exponent rules come into play here. Okay, let's go ahead and look at number 7. Now this is changing it up a little bit, isn't it? Because this looks a little bit different. All right, so we are going to just start out real quick. We're going to plug in all of our x values for our exponent, x, not just for our exponent, excuse me, but we're adding 2 to this exponent. Do you guys see that? X plus 2. So whatever x is, we're going to add 2, and that'll be our exponent. So 3 to the negative 3 plus 2 would be 3 to the negative 1, which we rewrite as, that's 3 over 1, so 1/3 to the first power, which is just 1/3. Okay, 3 to the negative 2 plus 2, which is just 3 to the 0 power, which is 1. 3 to the negative 1 plus 2 is 3 to the first power, which is just 3. 3 to the 0 plus 2 is 3 to the second power, which is 9. And 3 to the 1 plus 2 is 3 to the third power, which is 3 times 3 times 3, 27. Okay. When we go to graph this, I would suggest that if there's one point that's real far off like that, you don't worry about it. You don't need to change what you count by just for that one point, because otherwise that's going to cram all of these a lot tighter together. So we'll just go ahead. Let's go ahead and count by ones, because we do need to get all the way to 9. So we don't need to label it since we're going to just count by ones. So go ahead and create your x and y axis. And let's plot our points. Negative 3, and then 1/3 would just be a little ways up. It's tight. It's kind of hard. You'll just do your best. Negative 2, 1. Negative 1, 3. 0, 9. And you can see how this just starts jumping straight up, doesn't it? It's a very, very steep exponential function. It's very sharp.
So we don't have to plot the...
No, don't worry about the 127. Earlier today we tried to lower the x-axis, and there were about 26 lines above it, and we were able to, but it really doesn't make that much of a difference in the appearance. You can get an idea of what it looks like.
So in homework, we don't have to put,
if there's just one that's off, you don't have to count by something different. But if there's a lot of room, like the other ones were such small numbers, I would count by something different so that you can space it out a little better. Okay, number 8. All right, so we've got 1/4 to the -1 minus 2. 1/4 to the -3, which we have to rewrite this as 4/1, or 4 to the 3rd power, right? Right. 4 times 4 times 4.
64.
64, good. Okay, then 1/4 to the 0 minus 2 is 1/4 to the -2 power, which we write as 4 squared, or 16. 1/4 to the 1 minus 2, which is 1/4 to the -1, or just 4, or 4/1. 1/4 to the 2 minus 2, 1/4 to the 0 power is 1. And 1/4 to the 3 minus 2, 1/4 to the 1st power is 1/4. Okay. All right. So now 64 is way out of the question. I think we could accommodate 16 by doing what? Couldn't we just maybe lower the x-axis down here? Instead of having to change what we count by, we could just lower the x-axis, and I bet we can make it work. So we can still count by ones. There's 0, 16. 1, 4. 2, 1. And 3, 1/4. Now, it is going to always have a little bit of a turn, so even though it's kind of hard to see, you can see this where it starts to curve. Now, it's not going to curve back up, even though my line does slightly look like it starts to kind of come back up. It really doesn't. It just continues to get closer and closer to the x-axis. Okay. Number 9 says, which graphs 1 through 8 were exponential growth? Which ones do you think, when you go back and look at 1 through 8, would be considered exponential growth? Hannah?
1, 7, and 5.
1, 5, and 7. That would be correct. Exponential growth, because you can see how it grows, right? It goes up. That's exponential growth. Okay? All right, let's look at number 10. Number 10 says, and here's where you're going to start using your calculator. We didn't need our calculator until now, right? And you need to be able to do them without calculators until you are given permission to use them, all right? It says, use your calculator to make tables of x, y values for each of the following equations and use values for x from -5 to 5. So you already have it, your table set up, -5 to 5. So we are going to, bless you, we are going to use our calculator to plug in these numbers. All right, now everybody should have the TI-30XA, so I'm going to help you with plugging these in. Okay, hold on just a minute. All right, let's do this first. We're going to do what's in the parentheses first, okay? So we're gonna click 2, and then I'm gonna write this up here. So 2, and then click the Y to the X button. Then we're going to have to put in a -5, but the way we put that in is 5 negative. Do you guys know that? Okay, then go ahead and hit equals. And then we're going to hit times 3 because we still have to multiply by 3. Now, you're going to get a really long decimal. It's 0.09375. Yes?
Yes.
Okay, so we could write that estimated, or if we want it in a nice fraction, you are going to click the green second button up in the top left, and then go all the way down that column and click the arrow that goes this way that has an F with like an arrow, and a D. That means change from fraction to decimal and decimal to fraction. So if you click that, it turns it into a fraction for you. What does it become?
3/32.
3/32, exactly. 3/32. Isn't that nice how that works? Isn't that awesome? So cool. 3/32. Okay, so we got a lot of calculator work. So let's do this together, because the worst thing that could happen is you start punching the buttons in the wrong order and you just drill that into your head and you're doing it the wrong way, and then you're just going to keep winding up with the wrong answers. Okay, so here we go. Now, obviously, the number that's going to change each time is this right here, right? That number I just circled because we're changing the x value each time. All right, so here we go. 2. Then we hit y to the x. Then we have to hit 4 negative. And if I didn't tell you where the negative button is, it's right down there to the left of the equal sign. Okay, then hit equals times 3. Hit equals. And then we need to change it to a fraction, so we hit the green second button and then the back arrow. And that changes and gives us 3/16. Everybody should be trying this with a calculator. If you need to borrow one, you can get up. I know we're recording, but that's fine. Please, I want you practicing. Okay, let's do the next one. So we're gonna find out the -3. So we hit 2, y to the x, 3 negative, enter, times 3, enter. And when I say enter, I mean equals. And then the green second button and the back arrow. And we get 3/8. Very good. Okay, now we're gonna do -2. All right, so 2, y to the x, 2 negative, equals, times 3, equals, green button, back arrow. And we get 3/4. Good. I'm going to say one more with you, and then I'm going to let you go on them. 2, y to the x, 1 negative, equals, times 3, equals, green button, back arrow. 1 1/2?
Yes.
Okay, and you can write that as 3/2 if you want, or 1 1/2. All right, you're going to do the same thing. You're just not going to have to worry about hitting the negative now for the negative number. Okay, so go ahead and finish that. I'm going to finish it, and I'm going to put all my answers in here, and we'll check them. Actually, you might be able to do some of these on your own. 2 to the 0 power is what? 1 times 3 is 3. That one's easy. 2 to the first power is 2 times 3 is 6. 2 squared is 4 times 3 is 12. You don't need the calculator for this. I don't know. I think that's supposed to be a 3 there on your paper. Sorry. 2 cubed is 8 times 3 is 24. Okay. At this point, you might want to continue with the calculator.
That's helps because there's 2 2s.
Yes, I just had you guys adjust the 2 2s. Okay. So those are the numbers that I get for my table. Okay, I think you're doing pretty good. Just plugging those in. All right, let's go to number 11. It says use your calculator to make tables for each of the following equations. Use values for x from -5 to +5. Okay, the difference here is that now inside of our parentheses we have a 1/4, right? And so maybe that throws you off. Maybe it doesn't. Okay. All right, so here's how we're going to do this. Now, 1/4 really, I think, would be easier to just do 0.25. You could just do 0.25 and then just keep doing with what you're doing. But you may get to one where it's not an ending decimal, it's not terminating like 1/3, and you don't want to just go ahead and enter in 0.33 and stop when it's really 0.3333, you know what I mean? So you need to know how to do it with a fraction. So here's how you would do it with a fraction. Okay, there's some new buttons to use here. All right, so you're going to click the open parenthesis, and you'll see up in the right-hand corner of your calculator, it opens up the parentheses. Then you're going to click 1, and then right there to the left of the 1 is a little button that looks like this, A to the B/C. Click that, and when you do, it's going to give you this little symbol that looks like this on your calculator. Okay, that's the division symbol. Then click your 4, so it's kind of like a 1/4 but sideways. Okay, and then now you want your exponent, so we're going to click the Y to the X button, and we're going to do -5, so we have to hit 5 negative, then hit equals, then we're going to multiply by 6, and we get, times 6, and we get 6,144 if you did all of that correctly. Oh, yes, it will be exactly the same if you use 0.25. The reason that I wanted to show you all of that was because if you didn't have 1/4 in your function, let's say you had 1/3 as your function, you don't change that to a decimal form. You would have to know how to put it in as a fraction into your calculator if you're allowed to use your calculator, okay? So, anyway, I think you could probably continue on with that. I'm going to give you a few more. I don't think we need to keep practicing putting that in. You could, if you want to copy these down in case you need to practice so that you know that you're coming up with the right answers, then feel free to do that. Okay, we do have about 5 more minutes, so I would like to kind of see if we can't finish on through this lesson, okay? If you're watching this from home and you're in another class period, we did not get this far in one of our other class periods. Feel free to go ahead and finish the video, though, and you'll be ahead of the game. Okay, let's look at number 12. Number 12 says, if you see an equation of the form y equals a times b to the x, relating the variables x and y, what will the values of a and b tell you about the relation? What that means is if you have a function that looks like this, but of course you would have a number for a and a number for b, like up here. See how we have x and y, but a in this example in number 11 is 6 and b is 1/4. Do you see that? Okay. It wants to know what do a and b tell us about this function. Okay, so this is what you're going to take notes on this here. All right, so if b is greater than 1, then it's going to be an exponential growth. And if b is between 0 and 1, then it's going to, instead of a growth, it's going to get smaller and smaller like some of our other graphs did. And this is referred to as exponential decay. And then your A is known as your start value. What that means is, look up here in number 11. The start value here is 6, okay? So if this was saying, like, for example, if x is 0, like up in this function here, if x was 0, that would make this 1/4 to the 0 power, that becomes 1, right? And then 6 times 1 is just 6. So when x is 0, then you get 6. That's your start value, okay? All right, let's look at, I don't know if we're going to have enough time to do this or not, but we can look real quick. Under ideal conditions, the number of rabbits in a certain area doubles every 3 months. The function that gives the population at any time t in months, if originally there were 40 rabbits, is this function. Okay, so if there was 40 rabbits and it's going to double every 3 months, double, that's why it's times 2. So the starting value is 40 because there's 40 rabbits. Okay, eventually you're going to have to write these by yourself. So 40 rabbits, that's your start value. It's going to double, so it's times 2, and it's happening. It does this every 3 months. Well, the reason it's t divided by 3 is because it's happening every 3 months. So your time divided by 3. And then it says to complete a table of values, which we're pretty good with completing tables of values. I don't think we're going to have time to fill this in, but why would I want to choose, here's what I'm more concerned with. Why would I want to choose these as my values? Because they're divisible by 3, right? Very good. Okay. All right, and then real quick down here, if we kind of look at this, it's talking about spreading a rumor. How would you describe the rate of rumor spread for each graph? Look at series 1. Series 1 is, what kind of a function is series 1? It's linear. So just make a little note out here that says it's linear. Series 2, I don't know that I'd classify that. Series 3 would be what? How about what we just learned? Exponential, right? Exponential. Okay. And that answer's 15. 15 is series 3, right? Okay. All right. Wow. Well, that was good. Is this unit, what unit is this?